Hello everyone, good evening and welcome to this class. So we are continuing our solution series, and our today's subject is abstract algebra, and we'll do solution of all the problems from this particular topic of December 2023. So the topics covered are group theory, ring theory, number theory, all these three. If I talk about how many questions were there in part B, there were 4 questions, so 12 marks. In part C there were 6 questions, so a little bit exceeding its criteria. Generally algebra is of around 30 marks, you can say, but this time you can see that it is almost going to 40. So but then from the number theory you had 2 question extra, so you can just say the same thing again. So yeah, let's just start for today, shall we? So the pattern is same. I'll just solve one by one all of the problem in front of you from the exam in the shortest way possible. And if I look for the questions, there are questions from homomorphism, one question from Galois, basic number theory function, like you have a question from integer modulo properties, 2 of them. So let's just start. One very basic problem is here in front of you. It says that in any class of 50 students, which of the following one of the following statement is necessarily true, like should be. Okay, so there are 50 people and we have they are talking about birthdays. Okay, so we have 365 days, 65 days. Let's see, 2 students have their birthday on same day. It's not necessary. If the statement would have been that 2 statement have birthday on same day in a month, then we would select that option, because we have 365 holes and only 50 pigeons, so there will be many empty holes and no pigeons have to go into 2 holes. I mean, no 2 pigeons have to go into 1 hole. Every month has birthdays of at least 5 students. Every month has birthdays of at least 5 students. Every month, at least 5 students. That means they are setting the lower bound, that it should be at least 5. But again, if I said, from 1st Jan to like 19 Feb, if I set all of them in a way, so all 50 birthdays are exhausted, right? So there is no one whose birthday is in March or April or so on. So we cannot have a lower bound, we can have a upper bound. So these 2 options are gone. It says that there exists a month which has birthdays of at least 5 students. So they are setting at least lower bound, so this we'll have to look. The birthdays of at least 25 students are during the first 6 months. No, all the birthdays can be in November and December. So this statement is also false and your question is done. The correct answer is option number 3. But yet we will try to solve it. Let's see. There exists a month which has birthdays of at least 5 students. So I mean, we have 12 months. Okay, so let's say that we have x1, x2 and so on. We have we have how many students? 50. Okay, we have 50 students. Oh, sorry, let's just name it as month. Okay, so we have 12 months, let's say January, February and so on. and we want the sum to be 50, right? X1 is number of birthdays in January, X2 is number of birthdays in February, and X12 is number of birthdays in December. Okay, now if each xi is less than 5, then sum xi, I varies from 1 to 12, will never be equal to 50, right? Moreover, it will be strictly less than 50. So that means at least one of them must be 5, right? At least one of them must be 5. So this statement holds true. At least one of them must have 5. Let's move to the next problem, shall we? I hope it's clear to everyone. There is this problem that let G be a finite group. So first click in your head, it's a finite group. Which one of the following is necessarily true? So we have to find out the true statement. Okay, G is a union of proper subgroups. So proper, we have a problem with proper subgroups, right? If I take like, let's just take Z is equal to simply Z2, or what people call it as C2, which has only 2 elements, 0 and 1, then there are no proper subgroups. So this statement is gone, right? Trivial, and the group itself, we have only 2 subgroups. G is a union of proper subgroups if G has at least 2 distinct prime divisors. G is a union of proper subgroups if G has at least 2 distinct prime divisors. Okay, so we have that cardinality of G. So it's saying that G is a union of proper subgroup if G has at least 2 prime divisors. So let's say that P dot Q divide cardinality of G. Okay, G is a union of proper subgroups if G has at least 2 distinct prime divisors. So we have 2 distinct prime divisors for G. Now they are saying that G is a union of proper subgroups. Can we consider Z6 again? Right, I think we can just consider Z6. For option 1, this is the counter. For option 2, let's take Z is equal to Z6 and see what happens. I have 0, 1, 2, 3, 4 and 5. Okay, now I do know that 1 and 3 1 and 5, both of these elements will generate the whole Z6. So I cannot use the groups generated by 1 and 5. Okay, so what are the rest of the group? I have proper subgroups. I have 0. I have group generated by 2, which is 2, 4 and again 0. I have a group generated by 3, which is 3 and 0, and 4 is also. So I mean, I cannot, union of these subgroup is not Z6. So you can discard option number 2 using Z6. Now let's move to the statement number 3. If Z is abelian, so now we have a abelian group, then G is union of proper subgroups. We have many examples, right? 1 and 2, both of them works for example this option number 3 as well. So we can discard option number 3 using Z2, okay, or Z6. Now we have discarded 3 options. So we have our answer, which is option number 4. It says that G is a union of proper subgroups if and only if G is not cyclic. So now see, that's why the examples we were picking which were cyclic, we have used them as a counter examples, and they were working, right? So if you take a cyclic group, then you cannot write it as a union of proper subgroups, because if you will not get any generator of a group in any proper subgroup, right? If you have a proper subgroup, it cannot have a generator of G. So it does not matter how many proper subgroups all of you take, you will not get generated in any of them, and hence you will not get your whole group. Okay, so if you take a cyclic group, then it will create a problem, but that is not the case in case of non-cyclic. So I mean, I leave it to you to prove the other way. In case of cyclic, you will not get that I have proved, okay, simply because of the generator property. Let's move to the next problem. So I'm not going to give you the complete proof, I'm just giving you hints of the proof. This is also a fine problem. This is really a good problem. Okay, which one of the following is equal to 1 to the power 37 plus 2 to the power 37 plus 3 to the power 37 up to 88 to the power 37 in Z89? Okay, so I mean, I was working on a research problem recently, and just now I read this and I can think of that problem. Just right now I got this thought that okay, it is that problem. So first of all, you need to verify that whether your number 89 is a prime or not. And how do you verify that a number between 0 to 100 is prime or not? So what you do is, if it is between 0 to 100, then your one of the factor must be between 1 to 10, right? If it is not, then number is exceeding 100. One of the factor must be between 0 to 10, right? Because if none of them is between 0 to 10, then you have 11 multiplied by 11 at least, and that's exceeding 100. So if you look that none of the number 2 3 4 5 2 3 5 7 does not divide this number, so it must be a prime number. So we have a prime number. So whenever P is prime, so we have F89 precisely, right? A field of size 89, or you can say that it is Z89. It's same, Z89, and I am adding up all the elements of a field except 0. I am adding up all the elements of a field except 0. Okay, so one way to do is that this group is, this field has a generator, right? This field has a generator. The multiplicative group of a field is always cyclic, and you are adding up all the elements. Okay, and so you can look for any of the one generator, and then you can just simply proceed. Okay, so it's a cyclic group of cardinality 88, and you are adding up all the elements. Yeah, so basically you have a geometric progression. Anyways, I'll do it by both the ways. One way is that I do know that the inverse of any element in Zn, additive inverse of any element in Zn is n minus r, right? If you have element, the additive inverse of r is n minus r, right? Inverse of each other, and you can just start replacing it here. So 88, the inverse of 88 is actually 88 inverse is what? 88 can also be written as -1, can it? Yeah, it can be written as -1, right? 88 can be written as -1, or you can just simply look that 1 is the inverse of 88. That also works. 1 is the inverse of 88. Additive inverse, not multiplicative inverse. I mean, this would be the simplest explanation. I think we don't have to go too deep. So you see, 1 is a additive inverse of 88, right? Or you can just say it is -1, right? So you can rewrite it as -1 to the power 37, and this is 1 to the power 37, right? Similarly, you have 2 to the power 37, and 87 is -2 to the power 37. Okay, so you can just cancel them out, all of them, one by one, because of the odd power. You will get negative out, and you can cancel out all of them. So basically they are even number, so you'll get perfect pairs, like you have 44, all of them will cancel each other, so you'll get 0 in that case, because they are inverse of, this is inverse of this is inverse of this, somewhat like telescope and so on. Okay, good. And what is the other way? The other way is that if you have this is a very interesting result. If f be a finite field, and H be a subgroup of f star, where f star is what? The set of all units of f, or precisely f minus 0, because in case of field, 0 is only element which doesn't have multiplicative inverse. Then summation x to the power some constant, fixed constant, let's say this field must have a cardinality, right? Cardinality of f is equal to some p to the power let's say k, okay, and you have x to the power r, x belongs to h, so you are adding up all the elements, okay, yes, this is equal to 0 if r is not multiple of p, the characteristic p. That's it. Like, it need not to be 37. If you would have any number which is not 89 itself, in that case you will get 1 plus 1 plus, in that case also you are getting 0. No, you are not getting 0, you are getting 88, right? If you take power 89 here, 89 here, 89 here, in that case you will just get 1 plus 1 plus 1 88 times, which is 88. Otherwise you will always get 0. Yeah, good evening Pankaj. I hope you are getting it. And the proof follows from the simple fact that you are having a geometric progression, because H is a cyclic group and it must be written as a power of one element, and when you add them up, it's a GP, geometric progression, right? Like your field F is actually like this, right? You have field is like some a to the power 0, a to the power 1, a square, and so on, a to the power the cardinality of field, in this case it is 88, okay, this, okay. So if you add them all up, you are having a GP, okay, yes sir. Anyways, and if you take any power, that still remains a GP, so you will get sum of all the elements of a finite field will always be 0, and if you even take their powers, it will still remain 0 unless the power is actually not co-prime to the cardinality of the field. Okay, I hope you understood some of it. Let's move to the next problem, shall we? This one, consider a field C together with Euclidean topology. So it's just standard, you can just ignore that you ever read it. Let K be a proper subfield of C. So we need to take an example K, which is a proper subfield of C, all right, that is not contained in R. So basically that means we have an imaginary number in K, right? Iota or something like that. We have an imaginary number in this K, okay, which is not contained in R. That means that if you take whole complex plane, then your field is not just on this real line, it is somewhere on the plane too. Which one of the following statement is necessarily true? Which one of the following statement is necessarily true? So do we have any example of a subfield which is not contained in R, but it is a subfield of C? Yeah, I have an example. Like we can take Qi, right? Qi, Qx upon x square plus 1, that's a field, and it's precisely Qi. Okay, so it is not contained in R. It is just A and B both belongs to rationals. Right? Now, K is dense in C. Unluckily, the example which I have constructed is dense in C. So, I mean, this is actually satisfying the option. We can't say anything about it. Let's move to the next. K is an algebraic extension of Q, but the extension I have taken is actually algebraic. Okay, so in that case, we have to take another extension which is not algebraic anymore. So I can just simply take extension like by pi and I, right? Something like this. Extension of Q by pi and I. So this is no longer algebraic anymore. This extension over Q is not algebraic, but a this, what do you call it? Not algebraic. Okay, so it need not to be an algebraic extension of Q. It may be a transcendental extension. Let's move to the next. C is an algebraic extension of K. So C is an algebraic extension of K. That is also not true, because in this case you can just simply consider Qi. Okay, C is not an algebraic extension of Qi. It's not, right? Yeah, it's not, because Q pi I is on the way. So this is also gone. The smallest closed subset of C containing K. So now in our example, I have Qi. Okay, the smallest closed subset of C containing K, that means it should contain Qi closure, and Qi is actually dense in C, right? Q cross Q. We are actually having Q cross Q in R, which is dense in R2, right? Q cross Q is dense in R2. So this is kind of Q cross Q. So this Qi closure is whole C. So is not a field. So our Qi is working as a counter example here, because in our case it is C itself, and hence it is a field. So by just taking Q pi I and Qi, I can discard 3 options and select one option to be correct. Now why it should be dense in C? You can just simply use the fact that if you have a number, it's all multiples. You know, you will get all the multiples you will must have one imaginary number, and when you have one, you add them up. So like try to visualize them on the real line. It should contain Q at least, because the smallest field is Q, and you have I, so Qi will be there at least. So it must be dense in C. Okay. This problem, this is really good problem from part C. So we have solved all the problem from part B, 4 problems, 2 from kind of number theory, or you can say algebra only. Let's move next. Which of the following statement are true? So it's part C problem, and which of the following are true? That is the question. Let's look at one by one option and move ahead. G1 and G2 be finite groups. So we have finite groups such that the cardinality of G1 and cardinality G2 they are co-prime numbers. Then any homomorphism from G1 to G2 is trivial. It seems very trivial result as well. Okay. And why is that? Because if you have any element in the range, then you will have that property will have some problem. So let's say you have F, okay, from G1 to G2, and you have some element which is, so for any x belongs to G, order of fx, right? We have this result. order of fx divides order of x, right? This result we have, order of fx divide order of x. If order of fx is not equal to 1, that means it is non-identity element. This implies that order of fx, let's say it is equal to r, okay, equal to some say r, then look carefully, let's say it is equal to r. This implies r divides order of x, and order of x divides order of g1, right? And r is an element in g2, so and r divides order of g2 as well. So this implies that r divides order of g1 and order of g2. This simply implies that that GCD of order of g1 and g2 is not 1, it is at least r. But the question says that GCD of g1 and g2 is 1, they are co-prime, right? And if two numbers are co-prime, we cannot have a common divisor. So we are getting contradiction like this, okay, because we are getting that if order of fx is r not equal to 1, then we have that g1 and this cardinality of g1 and cardinality of g2 are not co-prime. So that's a counter example which works. Okay, let's move to the option number 2. So one we are saying that it is a correct option. Let's look at the option number 2, which is really looking interesting. G be a finite group and f is from G to G. It's a group homomorphism such that f fixes more than half of the element, like f of x equal to x for more than half of the element. Then it is just an identity map. So this is really interesting. Let's look at this problem, shall we? So the question says that f is from G to G and f of x equal to x for more than half element, है ना, more than half of cardinality G. Now let me just tell you this interesting result. Let's take a set S. Okay, I do know that f of G is a subgroup of, in this case we have only G is a subgroup of G only, right? Because it is a subgroup of range. Okay, and cardinality of f of G is greater than cardinality of G upon 2, which is given information. They are saying that more than half of the element of G are in the range. They are fixed, that is another scenario, but they are saying that more than half in the range. So fg is a subgroup of G and it contains more than half of the element of G. So the only possibility for order of fg is equal to order of G. So this simply implies that f of G is equal to G. So here we have just established one result, that whatever the range is, it is the whole group. Let's leave this fact here and move forward. If I take, okay, look carefully, if I take a set S equal to x belongs to G, all those elements such that f of x equal to x, all those elements which are self-mapped, under this homomorphism from G to G. First of all, identity belongs to G. First result, that E belongs to S, not G, S, because f of E is E. F of E is E. Second, for any xy belongs to S, f of x y inverse, because it is a homomorphism, I have f of x, f of y whole inverse. Okay, and f of x is, since x is in your this set S, so f of x is x only, right? Because it is self map, and again y is also in S, so f of y is y only, so y inverse. So f of x y inverse equal to xy inverse. That means xy inverse is also self map, right? Xy inverse is also self map. So if you take any x and y, xy inverse is also in S, so this S is actually subgroup of G. It satisfies the one step test, right? And cardinality of S is greater than cardinality of G upon 2. So the number of element in S is at least more than half, and it is subgroup, so this S must be G only, otherwise S is not a subgroup. Order of S must divide order of G. I hope it is clear. So the simple fact is that if you collect all the elements under a group homomorphism which are self-mapped, it forms a group. Okay, set of all those elements which are self-mapped under a group homomorphism forms a group. Okay, now that group is actually subgroup of your G only in this case, because it is from G to G, and subgroup of G contains more than half of the element of G. It must be G only, because there is no other subgroup which contains more than half of the element of its parent group. So that's it. Okay, so we have solved this problem too. So this must be an identity map only. Second is done. Let's move to the next problem. Third one, let G be a finite group only, nothing else, having exactly 3 subgroups. So we have 3 subgroups, all right. Then G is of order p square. So we have 3 subgroups. So it is a finite group. So cardinality of G must be some number n. Okay, it is a finite group. Now what are the possibilities? That let p dot q, 2 distinct prime number, divide our group G, or divide the order of our group. This implies there is a trivial group. Okay, there is a subgroup H1 of cardinality P, because for every prime divisor there is a subgroup. There is a subgroup H2 which is of cardinality or order Q, because Q is also a prime, and there is another subgroup which is G itself. So if you have more than 2 prime divisor for your group, then it has at least 4 subgroup. At least 4, maybe more, there can be more, but if 2 distinct prime divisors divide your order of group, then there will be at least 4 subgroups. Okay, but this says that it has only 3 subgroups, so this case is not possible. 2 distinct prime cannot divide your order of group. We are looking at option number 3. This is gone. So this n should be only a prime power. So this implies that n is equal to a prime power p to the power k. Okay, now if k is greater than 2, if k is greater than 2, then you have a subgroup of order 1, a subgroup of order p, a subgroup of order p square, and a subgroup of order p to the power k. So you have again more than 3 subgroups. So it cannot be more than 2. If you want only 3 subgroup, you must stop at p square. So if a finite group have exactly 3 subgroup, the order of that group must be p square only. So option number 3 is also a true statement. Okay, and how did we solve it? In first case, we assumed that there are 2 distinct prime divisor. Then we are getting contradiction because it is having more than 4 subgroups, or at least 4 subgroups. So that's a contradiction. So the order of the group must be a prime power, and when it is a prime power, we cannot have p cube or p to the power 4, because in that case we are getting more subgroups. The first theorem of Silo says that for any p to the power r divide order of group, there is a subgroup of p to the power r. So we will have subgroup of p square, p to the power k, and all the divisor of, you know, up to k. So we'll have at least k plus one subgroup. So statement number 3 is also true. Let's move to the final statement. Any finite abelian group G. So now we have abelian has at least dg, d cardinality of G subgroup in G, where dg denotes the number of positive divisor of M. Isn't this the Lagrange's theorem? The converse of it. It's true in case of abelian. The converse of Lagrange's is true in abelian. For every divisor, we have a subgroup. Yes. So we don't have to do anything about it. If they would have said non-abelian, then the statement would have been false. Maybe, or it would have been very difficult problem to solve. Converse of Lagrange's fails at A12. Right? Even non-abelian group up to order less than order 12 satisfy the converse of Lagrange's theorem. First time it fails at A12, A4. The order of A4 is 12. It doesn't have any subgroup of order 6. A4 does not have any subgroup of order 6. That's amazing. Okay, this is the first number. 12 is the first number where converse of Lagrange's fails. Okay, but in case of abelian it is true, and that I think you should know. So all the 4 statements are true. Correct answer is 1, 2, 3, 4. Algebra 2023 December. 40 marks. 40 marks. Okay, let's move to the next problem. Oh, sorry, where is it? Just let me get the next problem. It must be here. Yeah, let's look at this one. This looks like, you know, some tricky problem, and if I am in the exam, I'll tell you how I will try to solve it. There is you know, formula based approach, but I don't think that before this exam you would know that this formula was used in this question. So every time there is a question, people makes a formula for that question, and then they give you another question, and then you make another formula, and then they give you another question. Okay, so I mean, how can we solve it without using any formula? That's what I will try to do. Okay, so I have the question says that n belongs to Z. It's an integer number. We will look for natural because I'm more you know, comfortable with naturals. N is congruent to 1 mod 7. So simply my n can be written as 7k plus 1. Let's call it k1. 7k1 plus 1. So if I divide it by 7, I'll get remainder 1. Okay, k1 is an integer now, and at the same time n is congruent to 4 mod 15. So n is of the form 15k2 plus 4. So these two statements I have, straightforward. So I need to find a common solution for these two equations, and the best way is to look, because you are in exam and you have objective question, you look for options. If you can construct one common solution, it must work for all, because the question is asking for all. Okay, so let's try to figure out one common solution and we will be done with our question. Let's see. N is congruent to 1 mod 3. So n is of this form. If I divide it by 3, then I'll get 0 from here, because properly, you know, divided by 3, and 1 from here. So I don't have to do anything for this one. This is true either way. Okay. Now if I look for this, yeah, see, the Ratul is suggesting that if I take n equal to 64, the problem is done. But how do I get there? How do I get 64? Why should I take 64 only? Okay, so I look at options. So I look at 35 and I feel like it's a little big number. I will move to a smaller number. Let's look at 21, little bit smaller. So let's look at 21. So n is congruent to 1 mod 21. So I have 1 mod 21. Okay, so yeah, good evening Rawat and Ratul and rest of you guys. So 1 mod 21, that means my number is of the form 21 some, let's call it r plus 1. Okay, can I get this kind of number from here and here both? So I take 21 plus 1, which is 22. So 22 is working here but not working here because it is 7 modulo 15. So I increase r, so I take 42 plus 1. So this is not this is working for any this 7k1. It will always work for this. So all I have to do is look for 15k2 plus 2. Okay, so I take 3, r equal to 3, and I get 63 plus 1, and this number works. This is congruent to 4 mod 15, and it works for 7 anyways, because if you divide it by 7 you get 1. So 64 is your number. Now you look for rest of the answer. N is congruent to 1 mod 35. 64 is not congruent to 1 mod 35. This is true because this is what we have used actually. N is congruent to 1 mod 5. No, it's not. It's minus 1 mod 5, which is 4. So sorry, this is wrong, right? So correct answers are first and third. I hope it is fine. Okay, the formula working behind it is actually this. What do you call it? It's called Chinese remainder theorem. So you use that theorem and then you get the answer. But I mean, in exam, I don't think that you have to go through that approach. You have to look for options and try to find a common solution and then eliminate. Okay, but the next question is purely on the formula. If you don't know the formula, then this question is not for you in the exam. Okay, so the general approach is that we know that order of G, L, N, Z, P or FP, like cardinality, field of cardinality P. For this we have a formula, but we do not have formula for what? P to the power k, right? I mean, in general we do not have, but actually there is a formula. So the formula for cardinality of G, L, N, Z, P to the power k is equal to, okay, so how this formula actually works is that the matrix will be invertible if and only if it is invertible over congruent modulo P. Okay, and then you use some combinatorics to solve the rest of the problem, that how many possible ways are there that you can get matrix over GL and ZP. So the formula works like this. You have something like this. Okay, n to the power or p to the power. So first that you have to take the cardinality of GL n p. Okay, this, and yes, I know it is not the field, but still there is a formula, you know, which works here. For p to the power k we have a formula which is not the formula of you know, which is not that formula which we have used, but there is a formula. And then you take the prime p and k minus 1, k is this number, and multiply it by n square. So this is, I think this is the correct formula. So you all should know this formula now. Okay, so in this case you will get your correct answer. Now I think you can easily calculate. So if ZPK, there is this formula. In general there is no formula, but in case of p to the power k, you know, the matrix is invertible if and only if it is invertible over modulo p. Okay, so GL and ZP, and then you find possible ways. So you can easily find in this case your p to the power k is 3 square, and we use simply 3 to the power k is 2, so and n square is 4, so 3 to the power 4 multiplied by this GLN GL 2, right? 2 3. I think this you can all calculate. From here on you can take on. Okay, so now it's simple to solve. For this we have a formula, right? P to the power n minus p to the power, yes, p to the power n minus p to the power n minus 1, and so on, p to the power n minus 1, and then you divide it by, like, fine. I think you all know this formula. Okay, p minus 1. Let's move to the next problem. So this formula you need to note down and remember it if there is ever again question from this formula anywhere at any stage in your life. So there will be, in some exams there will be, I'm sure. So you need to remember this as well, not only for the field. Let us move to the next problem, shall we? Okay, the question is cropping a little bit. Yes, no. So you have, this is also a good question, a fine question from ring theory, not very, straightforward question. Zx equal to x square plus 1. So we know x square plus 1, it's zi, right? Everyone know that this is zi, I mean isomorphic to zi. Okay, so our R is actually isomorphic to zi, right? We take the root of this polynomial and that becomes our actual ring. So for this case it's I, so zi. R is isomorphic to a subring of C. Yes, Z is actually a subring of C, right? Proper subring. So statement 1, there is no issue. I mean, we don't have to look for the question further that it is a subring of C. Fine, there is no issue about this. Let psi from Zx to R be a natural quotient map. So what would be the natural quotient map? So we have this map psi from Zx to R. So simply, if you have any polynomial, here all the elements are polynomial, you will divide it by x square and then you will write the remainder. Okay, so psi of p of x is equal to, you will write the image will be px mod x square plus 1, you will write the remainder. Okay, and then this is your element which is working as a 0 element, right? X square plus 1. Fine. So that will be your image. Now I do know that this ring actually is isomorphic to Zi. So any element from here can be looked as an element of Zi. And how this map is defined, that whatever element you have, you will have polynomial here, this kind of polynomial, and you will evaluate that polynomial at I. Okay, because you want this x square plus 1 to go to this x square plus 1, you want this x square plus 1 to be a kernel of the homomorphism from here to here. So I mean, what I am actually doing is that I am taking another homomorphism phi, which is from R to Zi. Okay, and R is Zx upon x square plus 1. Okay, so you can write it here, Zx upon x square plus 1, Zx. And how this phi is defined, that phi of any polynomial p is equal to pi. I evaluate that polynomial at I. So now you can easily see that x square plus 1 is a kernel of this homomorphism. So this is another homomorphism. Now if you have an element here, we can pick that element from here and we can take that element here, and then we can get into Zi and we can look for more details in Zi. That's very interesting, right? So if you have an element image of psi, we can actually look at that element as an element of Zi in Zi by using the map phi. Let's move forward. Okay, I hope this is clear so far. Now okay, just give me a second. Now let's move forward. For any prime number p belongs to Z, if you take any prime number, the ideal generated by phi p. So what will be the ideal generated by phi p? It will be you take phi p, psi p. So it will be here. So you write p mod x square plus 1 and x square plus 1, and that will be just a prime number in Zi, right? Because first you find out phi p. Just let me get back there. So what you do is you take psi of p, which is actually it's a prime number. Okay, it's not a polynomial now. This is a prime number because the option says that for any prime number p. So it's a prime number. Psi of p is actually p mod x square plus 1 plus x square plus 1. Okay, and if we look correspond to this, we apply phi of p, okay, which is actually I evaluate this polynomial, which is a constant polynomial in Zi, so I'll get p only. So now we have a prime number p in Zi. So can this prime number generate whole Zi? No, it will generate p Zi, right? So this is the ideal generated by p is actually p Zi, because in a CRU ideal generated by A is RA or AR. Okay, what this is saying, that it is a proper ideal. Yes, it is a proper ideal. There is no doubt about this. Okay, because it's simply a ideal generated by it's simply p Zi in Zi. Fine. See, this is beauty of homomorphism. We are working in the ring R, but using homomorphism we can look at the same element in Zi and claim that in ring R. Okay, let's move forward. R has infinitely many prime ideals since our ring R is isomorphic to Zi. So now we don't talk about R, we talk about Zi. Does Zi have infinitely many prime ideals? Remember the result? If p is a prime number, p is congruent to 3 mod 4, right? Then ideal generated by p is a prime ideal. And how many numbers, how many primes we can have? Infinitely many. All the primes which leaves remainder 3 when divided by 4, like ideal generated by 7. Okay, and you can have many more primes which leaves remainder 3. So there are infinitely many prime ideal. Yes, that's a true statement. Okay, so it has infinitely many prime ideals. Let's move to the next statement. The ideal generated by psi x is a prime ideal in R. What do you think about this? Now you try to solve this. I will wait. What do you think? Is this a true statement? Ideal generated by psi x. So what will be ideal generated by psi x? See, this is not really so much technical. Ideal generated by psi x is equal to, psi x is what? It is x and since x is of degree less than 1, if you divide it by x square plus 1, you will get only x. So x plus x square plus 1, right? It will be x only, x plus 0 element, because if you divide it by x square plus 1, modulo x square plus 1 is only x. Now you take it into phi of this x is equal to I, because what was your phi? Phi of p of x is equal to p of I. Okay, now, and what is I? So phi of x equal to I is a unit in Zi. So ideal generated by I is what? Zi itself. Is it prime? Is it prime? Have I missed something? Have I? Seems like it is, right? If I take image of I have to evaluate it at I. So x is evaluated at I, and I is a unit in Zi. If I generate, right, that's what it is saying. The ideal generated by psi x is prime in R. So I have ideal generated by x. Okay, I mean, can we use another fact? If it is prime, then this, right? I mean, can we use this fact? Let me just look at this. I have zx upon x square plus 1, and I have a ideal of this, which is x upon x square plus 1, right? If this is a prime ideal, that's it. I mean, psi x is x only, so x upon x square plus 1. Okay, if this is prime ideal, then I have zx upon x square plus 1, okay, x square plus 1 is an ID which is also getting satisfied. I mean, I am getting this option to be a correct option. Is this a given answer? I mean, have I missed something, or is it fine? Let me just check the answer. No, fourth is not given. Okay, I will have to check again on the 4, because I mean, from both the way I'm getting it. It's a commutative ring with unity, and ideal generated by x is just x. Yeah, I'm getting it. I think I'll have to recheck on the option number 4. Okay, but all 3 are done. Okay, I'll update you back when we are doing next class, which most likely be tomorrow on complex. So we'll get back to this question again. Okay. All right. Okay. I mean, rest is fine, but this one was like. Let's look at next problem, or maybe our last problem for today, because we will not be doing the question from Galois. I'll have to recheck on this. The ideal generated by psi x is a prime ideal. Okay, I'll have to see what happened. Okay, just give me a second. Yeah, there is no issue about this as well. Okay, just erase all link on the slide. Okay. Yeah, let's look at the final problem for today. On that problem, I'll get back to you. Okay. Fx is equal to x square plus x plus 1 and gx equal to x square plus x minus 2. I can easily see that 1 plus 1 minus 2 equal to 0. So 1 is root. So g of 1 equal to 0 in integers, okay, or anywhere. G of 1 is 0 always. Okay. Which of the following statements are true? Let's see. For all prime number p, fx mod p is irreducible over zp. Okay. So what they are saying, that f is irreducible for all prime p. So if I look at 1, it is creating problem at 3 now. Yeah. So your f of x is equal to x square plus x plus 1. Since degree is 2, if there is a root, then it is reducible. If there is no root, then it is irreducible. That is good thing about a polynomial of degree 2. Okay, if and only if follows. Even 3, for 3 too. So I have f of 1 is equal to 1 plus 1 plus 1, which is congruent to 0 mod 3. So over z3 it is reducible because it has a root. So for all numbers it is saying 1 is gone. Let's look to the second one. There exists a prime number p such that gx mod p is irreducible in zp. That's very false, because 1 is root every time. Does not matter what prime you take, 1 is giving you 0 without, without anything. So this statement is also false. Gx is irreducible on q. No, it is not irreducible, it has a root. Fx is irreducible in q, that we know. X square plus x plus 1, everyone knows it's irreducible in q. In R as well, because roots are the cube root of unity. So the only correct answer here is option number 4. So this would have been considered as a easy question in your exam. It's easy. Okay. There is this result, if you all remember. If f is irreducible over over zp, over some mod p, then we claim that it is irreducible over q. Okay, you take mod p and then you check whether it is irreducible over mod p or not. If it is irreducible over mod p, then it is irreducible over q. So this statement is actually contradiction of what I am saying. So I mean, using that fact you can claim, because it is reducible over q. Okay, if there exists, this is if there exists, if there exists p, there exists a p. It's not like for every p. If there exists a p such that f is irreducible over zp, then f is irreducible over q. Okay. All right. So this question, option number 4, I'll have to look again. So I'll get back to you on this tomorrow. But rest of all of the questions, I think we were easily able to solve them. So that was all from my side in this session. If any of you have any question, you can ask. Otherwise, we will meet tomorrow with complex analysis. Okay, and when the complex finishes, we will do some random practice questions. Obviously, I'll bring some new questions, fresh questions. So you guys be ready for that. Anyone, any question? Algebra 40 marks. Right. This time I think it will be 30 only. Yeah, you are welcome. All of you guys, you're welcome. And see you all again in the next session then. Yeah, you're welcome.